Alright, so now we're getting ready to start the second half of calculus. The first half of calculus is basically this idea of introducing derivatives and, well, actually introducing limits so that you can then do derivatives, what a derivative is, and then all the how to take the derivative, which was in chapter 3, all the rules for derivatives, and then the applications of derivatives. So that was the first half of calculus. The second portion of calculus is what we call integration, which is more of an idea of where we're working backwards from a derivative, that we're going to be taking antiderivatives, and the process of taking antiderivatives is called integration. So now a couple of notation things before we get started. Now we're kind of changing our perspective. Instead of me giving you a function f of x and asking you to find its derivative, I'm going to give you a derivative. And what, you may not like this, but they're just simply going to name the function that they give you as f of x. Except what you're going to have to remember is that this f of x is the derivative of some function. Now, obviously, we can't call this function that it's the derivative of little f of s, so they decide to come up with another notation, which is, in addition to keeping straight whether you have f and g in the problem, now you're going to have to keep straight with capital letters. If they give you the derivative as f of x, then typically we're going to say the function that it was the derivative of, we will use capital F. Okay, so in this notation, capital F of x would be considered the original function, and the derivative of capital F of f prime of x, is going to be this given function little f of x. And yes, it is going to matter when you are doing your free response whether you write the right capital F or lowercase f when you are doing these problems. Now, the idea here is that you're working backwards. That if I tell you the derivative is 4x cubed, then your job is to tell me what the original function is, to work backwards between what we were. And this one's pretty easy, that if you got a derivative of 4x cubed, it must have been x to the fourth, would have been what you were taking the derivative of. So you can, by intuition, which is basically know the rules going forwards, which means you also know the rules going backwards. And what we have done by working backwards is we have found, and I am going to highlight this because this is an important comment to make, we have found an antiderivative. We have found one of the antiderivatives. Now, why do I have to say one of the antiderivatives? Because what we're basically looking at here is this idea that a function, capital F, is called an antiderivative of f if its derivative is f of x. And that has to be true for all x in the interval I, and that basically is going to be our domain of interest. Now, why could there be more than one? Okay, the idea here is to remember that there's one very important function that when you take the derivative of it, you get 0. And so we don't know if, when we're looking at the antiderivative, we don't know if it was simply x to the fourth, but it could have been x to the fourth plus 2, because the derivative of the 2 would have been 0 and it would have dropped out. Or your derivative of 52 would go away. That all of these are possibilities, because in each case, when we take this derivative of capital F of x, take the derivative of the antiderivative, we get this 4x cubed. We call these basically a family of antiderivatives. That the antiderivatives are, there's infinitely many of them based on our constant. Okay? And that's why when we talk about the general antiderivative, we always recognize that our function, the antiderivative, capital F of x, plus a constant, will give you what the original function is, what the original y equals was that you started with. We don't always know enough information to determine what this c is, but that is something that we want to talk about, that if they ever ask you for the general antiderivative, then what you want to do is say it's the antiderivative of what you have plus some constant. Some constant. We'll do problems later where we actually have to find this. So if you take a look over here at the right, these are all antiderivatives of x squared. Now this is where you have to be careful. Don't get confused. The derivative of x squared is 2x. I want the antiderivative. I want to undo the derivative. And so you can start to kind of, with the power functions, it should be easy. When you take the derivative of a power function, the derivative of x to a power with respect to x, if you will recall, all we did was multiply the power in front and take the x and then subtract 1. So if I want to take the antiderivative of a power function, you can work backwards. Instead of subtracting 1 from the exponent, you add 1 back in. So instead of a 2, it must have been a 3. And then instead of multiplying by that 3, that exponent, you should have divided it because you're working backwards. So we are kind of using an inverse process when we're doing this. Hopefully you can see that the antiderivative of x squared would be x cubed over 3, or 1/3 x cubed. If I were to take the derivative of 1/3 x cubed, then I would get x squared, which is why, working backwards, the antiderivative of x squared is 1/3 x cubed. We'll say stress and antiderivative. And that you could have any constant that's added here. They all have the same derivative. So here is my family of antiderivatives of x squared. That there are infinitely many of them, and they all have this constant of integration. And they're pretty particular about this. When you do this general antiderivative, if you don't put plus c, you typically lose one of your free response points for that. So you got to remember to put that one in. Alright, so let's take a look at example 1 here. And again, this is just working backwards. If I got a derivative that was 2x, and I want to work back to its antiderivative, capital F of x, and they're asking me for general, I first start by just trying to reason out. This is x to the first power, so it must have been an x squared. And if I were to multiply, what constant would have to be in front of this to get 2x as its derivative? Well, just x squared. And then we want general, so plus c. So this would be our general antiderivative. Now you want to get in the habit of paying attention to notation. Now here in this one, they didn't call this f of x, they called it f prime of x. So the antiderivative of f prime of x would be little f of x. So you want to match your notation to the notation that they use. And what must that have been? Now again, you need to have an x squared in here because the derivative of x squared would be an x, but this would have a 2 in front of it like I did over here. So what I see is that I don't want to have a 2 in front, I want to have nothing in front, so there must have been a 1/2. Notice that I added 1 to the power 2 and then I divided by that power instead of subtracting, multiplying, and then subtracting 1. So we're doing the reverse process in your power functions. Alright, so let's see if we can take that reverse process over here. And again, they named it f prime of x, capital F. So the antiderivative, I totally forgot, plus c, they're gonna get you on that. It's always the easiest thing. You're like, ooh, I did the hard work. I took the antiderivative and found one of them, but you always forget that you got to do that plus c in order to get the general case in there. Alright, let's take a look at the next one. They named it capital F prime of x, so its antiderivative, I'm going to come down here for a little bit more room, would be capital F of x. Now, what we did here is we add 1 to the power, and then we divide by that power. Notice that if I add 1, I get 2, and then I divide by the power, 2 over 2 gives you 1. Over here, I add 1 to the power, 2, and then I divide it by it, which is the same as multiplying by 1/2. So over here, I'm going to take my power, I'm going to add 1 to reverse the process. Adding 7 over 7 to 4/7 would give me 11/7. And then I'm going to take the constant that's there and I'm going to divide by that power. which is going to give me, I probably should give myself just a little bit more room here. I'm not going to put equals there because I need to do plus c, and then now I'm going to simplify it. 2/3 divided by 11/7 would be 2/3 times 7/11, and that would give me 1433 x to the 11/7 plus c. Now, the good thing about antiderivatives is in simple cases like this, you can always check your answer because you can check that you got a correct antiderivative by simply taking its derivative. Take the derivative of f of x with respect to x and see what you get. If I were to take the derivative, I would get 11/7 times 14/33 x and subtract 1 from your power, 4/7 plus 0, and if you double check, you see that the derivative of this is going to be a 3 and a 2, 2/3 x to the 4/7, and we're correct. When you are looking at your general cases, let's come over here to this g prime of x. The simplify early and often is going to kind of come into play here, that I'm going to rewrite this before I even start as x to the -2. So that way I can do the antiderivative of this by saying that the little g of x, that would be my notation for the antiderivative. I'm going to add 1 to my power. -2 plus 1 is -1. And then I'm going to divide by that -1. So dividing by -1 is the same as multiplying by a negative. So we end up with plus c, 1/x plus c. Now, if you want to test it out, again, you can always check it by taking its derivative. So if I take the derivative of g of x with respect to x, we get the derivative of 1/x. If you want to do low d high minus high d low, you can do that. Low d high minus high d low all over low squared, or -1/x squared, which is going back to, oh, I forgot my negative. I lost the negative from this line to this line. So the minus -1 times 1. So it ends up being plus x squared, and it works. Okay, see, catch your mistake by that. All right, and then we get into the trig ones. The power functions are nice and easy. You're just working backwards. Now we get into trig. Now, we are basically asking ourselves, if dy dx is your derivative, then your antiderivative is y. And what do I take the derivative of and get cosine? The derivative of sine is cosine. So the antiderivative of cosine is sine of x, and because we're going for general, we do plus c. All right? So really, the hardest thing about this is paying attention is whether are you taking a derivative or are you taking an antiderivative, and make sure you have your main rules that we learned in chapter 3, that you have them working forwards and backwards, which is all we're doing. Okay? So here's a little summary of the antiderivatives that you basically need to know. If I have a constant times a function, and this is my derivative, then the antiderivative would still be the constant times the antiderivative. Because when you take the derivative, okay, kind of showing you the other way, the derivative of a constant times a function, the derivative, the constant pulls out, and we have the derivative of f of x, which is your little f of x according to our notation. So taking the derivative of this gives me this, taking the antiderivative of this gives me this. So that sort of makes sense, because the derivative of a constant times anything is the constant times the derivative, so the antiderivative of a constant times anything is the constant times the antiderivative. If I had the derivative of a sum, I would do the sum of the derivatives, and it does work the same way. If I have the sum of the derivatives, then I'm going to do the sum of the antiderivatives. Now notice that on all of these, I am not calling these general, I'm calling these a particular antiderivative. one of the antiderivatives. If we want to turn this into the general case, we would do plus c, but we just didn't want to write plus c on these. So we're just doing the particular one antiderivative, not taking into account the constant yet. All right, here's our power function. X to the n is the derivative. So I want to take the antiderivative. So taking the derivative of power function, you subtract 1 from the exponent and multiply. So working backwards, you should add 1 to the exponent and divide by that. All right, so that gets us to here. This one you just need to know, and you got to be very careful because you're going to be tempted. Notice that this says for all power functions except n equal to -1, because that's your 1 over x. And the antiderivative of 1 over x is your natural log, because the derivative of natural log is 1 over x. Now you might be wondering kind of here, why do we have these absolute value bars? And the answer is because you have to have a domain, relevant domain in this problem. That this is true, they're both the same. It doesn't matter. The domain of this and the domain of that will be the same. The domain of this and the domain of this will be the same. The domain here and the domain here will be the same. Okay? But here and here, the domains are not the same, because if I would be tempted, right? Technically, if I had 1 over x as my derivative, where x is greater than 0, that's what matches natural log of x, because there's a domain restriction here. X is only allowed to be positive. So technically, when we were doing the derivative, we already knew that the domain of natural log of x was 0 to infinity. So even though we might not have written this part of it, it was really only 1 over x for positive values. So if I'm not given a domain restriction here, basically we're saying x is basically not equal to 0, that's the only division by 0 problem that you have, that in order to do that, I've got to make the domain of the antiderivative match the domain of the derivative. And we put the absolute value bars in, because then that allows us to take the log when x is negative, because it turns it into a positive. And that's something you do want to remember when you are doing the antiderivative of 1 over x. It's natural log of absolute value of x. Of course, the easiest one, e to the x. The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. Your derivative of sine is cosine, so your antiderivative of cosine is sine. Nice. But now here's where you have to be careful. The derivative of cosine is negative sine of x. But notice that when I am doing the antiderivative of sine, notice there's no negative in front. So we basically have to think of this as the opposite of the derivative of cosine of x is sine of x. So we still have to take into account that there was a negative when I took the derivative, but it's missing. So this must actually be the negative of the negative sine of x. And the antiderivative of negative sine of x is cosine of x, and then we have an extra negative in front of that. This is where you get a little confused, because you've got to really make it clear whether I'm taking a derivative or whether I'm taking an antiderivative. These are again your trig rules, just working backward. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. The derivative of secant is secant x tangent x, so the antiderivative of secant x tangent x is secant. The derivative of inverse sine is your 1 over square root of 1 minus x squared. Your antiderivative of this fraction is inverse sine, and your antiderivative of this fraction is inverse tangent. So it's basically kind of like playing Jeopardy. I'm giving you the answer, the derivative, and your job is to go, what was a particular original function coming back? All right, let's take a look at example 2 here, kind of to show you we still have this simplified to make things easier. I want to take the antiderivative of this function right here. Now, right now, at this moment in time, you can only take the antiderivative of known derivatives. In other words, we have not done any work yet on how to work backwards in a product rule or a quotient rule or a chain rule. All we're doing at this point in this section 5.1 is working backwards for the derivatives that we have listed up here. So if the derivative you are given is not in a form that is a constant times a function, the sum of two functions, an x to a power, 1 over x, e to the x, cosine, sine, secant squared, secant tangent, and these two fractions, if it's not one of those, you need to make it look like one of those. We'll talk about what to do for the more difficult derivative rules later. What we want to do now is just manipulate it to get it to look like the known derivative rules that you have, which will mean that you know how to do the antiderivative. All right, so the first thing I'm going to do is rewrite this. The 4 sine of x does not bother me. However, this fraction thing does, because I don't have a work backwards from a quotient rule problem. But I notice that I have a sum and difference over a single term, which means I can split this into 3 separate terms. And I'm going to also rewrite everything with powers. So that's going to give me my derivative in the form 4 sine of x plus 2x cubed minus 1/2 minus 1 x to the negative 1/2 plus 1. And so when I go to take the antiderivative, and notice it says all, so this means we're finding general, so make sure you do your plus c. So g of x is the antiderivative, right? Antiderivative. And the antiderivative of a constant times a function is the constant times the antiderivative. The antiderivative of sine is your negative cosine, because the derivative of cosine is negative sine, so we need that negative, plus antiderivative of power function. Add 1 to your power, divide by your power, and bring your constant along. I'll simplify in the next step. Minus, add 1 to your power, divide by your power. Okay, I'll simplify in the next step. And then the antiderivative of a constant. The antiderivative of a constant. What? The derivative of what is 1? The derivative of x. I don't know why I don't have that in the list up here. So let's add this in, because that's an important one to know. If I have a constant, the antiderivative is always cx. I guess technically they're assuming that this is this case here because it's x to the 0. So I add 1 to the power and divide by 1. So it works out. All right? So that was in that power case. And then we just simplify. So, and I'm not done because I always forget, plus c. So my general antiderivative is negative 4 cosine x plus 1/2 x to the 4th minus 2x to the 1/2 plus x plus c. And then if you want to, I'll leave this for you. You can check to make sure that this is the correct antiderivative by taking this derivative and making sure I can get back to what I had before. All right, let's take a look at the next page. Here's another one. Now this one is a little different, okay? Now when we're given a derivative, we like to call these differential equations, because the derivative is your differential in y over your differential in x. Now, one of the things that we start talking about, and this is the most tip of the iceberg on these differential equations, is that in order for me to find a general and a particular solution to a differential equation, what we mean by this is to find a general antiderivative, that's a solution to a differential equation, and then a particular antiderivative, in other words, which one of the many must you be on, must the antiderivative be given some what we call initial condition. And that doesn't mean when time is 0. It just means you're given a piece of information. I'm going to be given this information about the original function. Now, if we look back at our picture that we had of the family, would you agree that once I know that basically because this is nothing more than a vertical shift up or down, that these are all kind of running parallel to each other, okay? The slope here and the slope here are parallel. The slope here and the slope here are parallel. That they're running parallel to each other. So once I tell you that f of 2, okay, equals 3, if I give you a point on the graph, 1, 2, and then it equals 3, once I give you a specific point, then I'm basically telling you which one of the general antiderivatives you are on. So this would make this given 2, 3 on the original f of x, I know which of the many that I am on. I am setting it. So you have to know, when you are solving, to get a particular solution, some initial condition, which is going to be this. So to start out, you always find the general solution. Your general solution, aka your general antiderivative, you just take the antiderivative. You find f of x, again notation, this is f prime, so I'm going to use little f. The power function, so I take my power and I add 1. I divide by that power, and I bring my constant, plus c. So the general solution, f of x, is going to be x cubed plus c. That's your general solution. Your particular solution, how do I figure out which one I'm on? We're going to use the fact that f of 2 equals negative 3. So if this is my given initial condition, then using my general, I know that f of 2, which is going to be 2 cubed plus c, has to equal negative 3. And I can basically just solve for c. c plus 8 is negative 3, so c in this case would be negative 11. So the particular solution, the one that you are on given this point, is going to be my x cubed minus 11. That's the curve in the family that I'm on. All right. Now, the differential equation in example 3, and this is kind of previewing, this actually doesn't come in until chapter 6. But it's called a separable differential equation, and the reason it's called separable is because you can separate the x and the y variables. That basically when I'm looking at this, okay, you kind of want to think of this as in differential form. And again, this is a preview of coming attractions. That if I had the derivative of y with respect to x equal to 3x squared, I can write this in its differential form, dy equals 3x squared dx. And notice that I have separated. This side is all the x's, and this side is anything that has to do with the y's, of which there's only one, dy. If you can separate a differential equation into y's on one side, x's on the other, it's called separable. And that always basically means that it's really easy to show and find the antiderivative of those. Okay? And again, so here's my derivative, and then we rewrite it. This is what we show the separation of variables. This is going to be a necessary step. We show the separation of variables by putting it in its differential form. Okay? And we'll talk more about kind of how this comes into play. A little bit about why you're looking at this here is that you're trying to find this original function, right? You're trying to find the y values. And for each original y value, you're going to be able to find this part right here, which is the differential in y, and then you have to add the constant to it, because you basically think about that where you currently are, think of it as y as your position function, would be your change, the net change that you have, okay, think of that, the net change that you have, which is going to give us the antiderivative of f of x, your net change at any x, plus some kind of constant that is due to where you were originally, So that's kind of this idea of where the c comes in. And we're going to talk way more about this in the coming sections. All right, the process of finding the antiderivative of each side is going to be what we call indefinite integration. And we want to have a symbol for that. So not only do we want to be able to separate it, here's our separation step, f of x dx. I don't want to have to say the antiderivative is, and then say it, so we gave a symbol. And the symbol is going to be, it's a little kind of S notation. It's really a summation notation, and you'll start to see why this integral symbol and summation are going to be the same. This is actually a capital sigma. That this summation notation, we'll come back to the summation part, we're taking the indefinite integration of both sides. The indefinite integration, you always have the antiderivative of dy becomes y, and then that y is going to be a general kind of antiderivative that you have to take a specific antiderivative and then add a constant of integration to account for where you are shifted up or down, which particular one that you are on. So when we talk about notation then, this is the anatomy of your indefinite integral. It always requires an integration symbol. It requires that you have your integrand, which is your derivative of some f of x, okay, where f prime of x equals f of x, right? And the dx is your variable of integration. And that's nice to know because you really kind of need to know whether you're integrating with respect to x, you might be integrating with respect to r. Think about your related rate problems where you were taking derivatives with respect to time. So I need to know whether I'm working backwards with respect to time. So I definitely need to know what my variable of integration is. All three of these parts are absolutely necessary to get your communication points. If you do not have an integration symbol, you do not have a dx in there, think of these like kind of parentheses that bookend the derivative that you're given, that we want to have them with this integration symbol. So if I come back to some of these prior problems that I'm doing using this notation, up here we would basically take this problem and we would have dy equals 3x squared dx. Then we would integrate both sides with respect to this x, which is giving me y equals x cubed plus c. So we're not going to do this in our head to get our communication points. We have to separate. We have to say, hey, I'm integrating. And then we have to give our general antiderivative. Okay? And then we come up and we use a particular solution the same as before. So that's kind of the idea of introducing some new notation for this section. Alright, so let's use that, and we're going to find a particular solution to the following differential equation. Now again, I still have to think of this in terms of the separation. So the work that we would show for this, dy dx equal to e to the x plus 20, and I'm going to rewrite this as 1 over 1 plus x squared. Because remember, we don't have a working backwards from chain rule. We're only recognizing derivatives we already know. And when I see this and I recognize that that's that fraction, that is one of those inverse trig functions. All right, I'm going to separate my variables. And it might be a little tedious for writing, but we want to make sure we get our all full points on a free response. So we show that we put the derivative in a nice form. Then I separated my variables. I wrote it in differential form. Now I am going to take the indefinite integral of both sides. A lot of times we come in, we simply just add our integration symbol in right there. It's perfectly fine. Save you a little bit of writing. The antiderivative of dy is always y. And then our antiderivative of e to the x, nice one, e to the x. Bring our constant down. The antiderivative of 1 over 1 plus x squared is inverse tangent of x. And then remember, you have to always start with the general plus c. And then you're going to use your given information to find c. So we're going to use the fact that when x is equal to 0, y is equal to negative 2 to find the constant of integration. So this step, there's my general. Now I'm going to say when y of 0 equals negative 2, then y of 0 is going to equal e to the 0 plus 20 inverse tangent of 0 plus c, and I would get negative 2. E to the 0 is 1 plus the angle whose tangent is 0, so that's 0, plus c equals negative 2, so c equals negative 3. Therefore, my particular solution is y equal to e to the x plus 20 inverse tangent of x minus 3. And then that's how we work these separable differential equations. All right, now let's take a look at a few more kind of examples of these differential equations. Now notice that in this one, I didn't give you the first derivative, I'm giving you the second derivative. So if you think about this, if I want to find a particular solution, we're still trying to find y. We're trying to find the original. So notice that you're going to have to actually separate and integrate twice on this problem. So let's take a look at it. Let's bring down my second derivative, and I'm going to go ahead and separate. And I'm going to separate by moving only one of the dx's to this side, because I have to separate once. Okay. And then I'm going to integrate. Now, when we integrate, and then integrate here, the antiderivative of the second derivative is going to be the first derivative. Okay, maybe it might be a little bit helpful. Maybe I'll rewrite this. Let's I think this might explain better what I'm doing here. That the second derivative is the derivative of the first derivative with respect to x. Okay, and so when I am going to rewrite this, I wanted to back up, I want to be a little bit more clearer there, that when I want to separate this, I'm taking the derivative of dy dx and 12x squared plus 6x minus 4. So I separate the first dx to this side. Okay, and so then we integrate. The antiderivative of the first derivative is dy dx equal to, then I'm going to run through this one, add 1 to my power, and you can start doing this in your head, and I divide by 3, 12 divided by 3 is 4, add 1 to your power, divide by 2, 6 divided by 2 is 3, 4x, and then plus c. Don't forget to put your plus c in there. Now at this point, since they gave me some information, I'm going to go ahead and find this first constant of integration using this given information. So that's a general solution for the first derivative. So that's a general first derivative. Now I want to find a particular first derivative when y prime of 1 is equal to 3. So y prime is just another notation for dy dx. So y prime of 1, 4 times 1 cubed plus 3 times 1 squared minus 4 times 1 plus c has to be 3. And this is going to give me 4 plus 3, 7 minus 4, 3. 3 plus c equals 3. So c in this case happens to be 0. So right now, after this first step, I am at that dy dx, the particular solution, particular first derivative is 4x cubed plus 3x squared minus 4x plus c. Now I'm ready to separate and integrate one more time. So dy is equal to 4x cubed plus 3x squared minus 4x. Oh, the particular I've found c to be 0, so that goes away. Dx, don't forget these parentheses. We are going to show we're integrating, so we integrate. Y equals, just repeat the process. Add 1 to the power and divide. Add 1 to your power and divide. Add 1 to your power and divide. 4 divided by 2 is 2. Don't forget your plus c. And then I go, oh, I have another initial condition. Notice that if I have to integrate twice, I got to have 2 initial conditions. Y of 0 is negative 6. So that's my general. So now we're going to go to the particular. Y of 0, which is going to be 0 plus c, is equal to negative 6. So c equals negative 6. So our final answer, our particular solution, is going to be y equals x to the 4th plus x cubed minus 2x squared plus minus 6. And then we're done with this problem. All right, let's take a look at the next one. Notice that here I didn't give you any information about the derivative. I only gave you information about the original, but I did give you 2 pieces of information. So when I do this, still using the same one, the first step is the same. The dy dx is going to be 4x cubed plus 3x squared minus 4x plus c. Now what's different about this is I don't have any information that is going to help me find c yet. I am just going to go ahead and separate and continue finding another antiderivative. So we separate, we find the antiderivative, so y equals, now notice that it will come out to be the same as what we had before. We are going to add 1 and divide by 4. We are going to add 1 to the power and divide by 3. We are going to add 1 to the power and divide by 2. And then I'm going to add 1 to the power. Remember, this is a constant, so plus cx plus, now maybe we want to, I can't use c twice, right? You can't use c when they're 2 different constants. Let's call this c1. And then I can go plus c2 because I need the constant of integration for the second indefinite interval. And so now what I'm going to do is I'm going to use both of my pieces of information. I'm going to start with the y0 equals 1. So I take this general that has 2 constants in it, and I go y of 0, which is going to be 0 plus 0 plus 0 plus 0 plus c2 is going to be 4. So c2 equals 4. That gets me to y equal to x to the 4th plus x cubed minus 2x squared plus c1x plus 4. That gets me halfway there. And then I use the other point, y of 1. 1 plus 1 minus 2 plus c1 plus 4 has to equal 1. So we end up with 2 minus 2, so c1 plus 4 equals 1, c1 equals negative 3. So my final answer in this case, given those initial conditions, would be y equal to x to the 4th plus x cubed minus 2x squared minus 3x plus 4, and that would be my final version. All right, a couple last problems here. I'm going to duplicate this just so I can have more room now that I've written on this side. Duplicate. Just waiting for it to go. And let me clear off all the writing that I did and come down here. Now let's take a look at this. Life does not always come packaged neat and pretty into derivatives that you already know. Remember, just like in the problem that we did in example, in this one, this was not a pretty derivative. I had to make it pretty by turning it into derivatives that I know by separating it out. The same thing is going to be true for some of these trig things. And this is where your trig identities come into play. We don't know anything that has a derivative of sine over cosine squared. So our job is going to be basically to rewrite this into something that we do know the derivative of. And realize you only have limited numbers here. You've got the ones that were on this page. These are the derivatives and antiderivatives that you are given, that you are using in this section. So I need to do some magic, some trig manipulation to get this into something I know. And hopefully if you ponder and take a look at this for a little bit, you'll see that I can kind of split this into a sine x over a cosine x times 1 over cosine x dx. And that by recognizing that, you realize that you have a tangent x times a secant x dx, and then you recognize that that is one of the derivatives that you should know from this list. That when the derivative is of the form secant x tangent x, it was the derivative of secant of x. So you will have to do a little manipulation on some of the ones that you're looking at. In this section, you should always pause and say it has to be one of the ones that I know the antiderivative of. So secant of x, and then don't forget your plus c. When you see this, this is always the general antiderivative until they give you information to help you find c. Right? And so, and again, just notation, usually we consider this to be the f of x dx, and so we usually call this capital F of x. Right? And same thing over here. It doesn't necessarily bother me that I have a p here, because tangent squared, and I'm taking it with respect to p, that is a derivative I know. Tangent squared is the derivative of tangent of x. Well, tangent of p, because that's my variable that I'm taking the derivative with respect to. So this is going to be your tangent. Or let's double check that before I do this. I was getting ready. I'm telling you something bad here. This is where you get confused. Oh, I don't know. Tangent squared's not one of the ones I know. Darn it. I only know secant squared and secant x tangent x. So now I come back to this and go, got to do some kind of trig manipulation before I start jumping to, I don't know anything that has a derivative of tangent squared. So I go, all right, what do I know? What trig identity might be useful here? Here I used a quotient and a reciprocal identity. So over here, it's a squared tangent. Maybe I can use a Pythagorean identity. Remember your Pythagorean identity? Sine squared, I'll do p, plus cosine squared, p is equal to 1. And then if we divide everything by cosine, this would be tangent squared p plus 1 equals secant squared p. So let's do a little trig substitution. I don't know anything that's derivative is tangent squared, but I definitely know some things whose derivative would be secant squared. And the minus 1's not going to bother me because that's a constant. So I'm going to rewrite this as secant squared p minus 1 plus 4 dp. And then we're going to have the antiderivative, or indefinite integral, of secant squared p plus 3 dp. Now I can do the antiderivative. Secant squared is a derivative I know. Secant squared is the derivative of tangent. So now I can work backwards and do tangent of p plus, be careful here, 3p plus c. Remember, you got to get that plus c in. And so again, we're considering this to be the antiderivative or indefinite integral. Whoops. We'll do f of p dp. So I'm going to call this capital F of p. Right? And so that's your introduction to antiderivatives, your indefinite integrals and your notation for that, and a little bit of introduction into what we call differential equations and how we solve them.